Okay, so you're welcome once again, and we are going to be looking at chemical equilibria today. I remain Anjoni Oluwafemi Excel, and I'll be your teacher for this particular lesson. Let's look at the objective of our lesson. By the end of this lesson, students should be able to define chemical equilibrium and identify its key characteristics, differentiate between reversible and irreversible reaction, distinguish between dynamic and static equilibrium, identify factors that affect the position of equilibrium, including temperature, pressure, and concentration. Then apply Le Chatelier's principle to predict the direction of shifts in equilibrium, and distinguish between homogeneous and heterogeneous equilibrium with appropriate examples, okay? And also to be able to write correct equilibrium constants expression, that's KC, for given reactions, and explain the significance of equilibrium constants in determining the extent of chemical reactions. So these are what you are supposed to have, you are meant to learn, or you should be able to understand as we go through the lesson. So let's jump right into the lesson now. Okay. We start with a definition of chemical equilibrium now. So we start with the definition of chemical equilibrium by saying that chemical equilibrium is a key concept in chemical reactions, especially reversible reactions. Many reactions don't go to completion, but reach a state where products and reactants coexist. Now, understanding equilibrium helps predict how changing conditions can influence product yield. Okay. Okay, that's just like a kind of synopsis, like an introduction to the main work itself. Okay. If we want to define chemical equilibrium, we refer to chemical equilibrium as the state of a system in which the concentration of reactants and product concentration do not change with time, and the system does not display any further change in properties. So that is what chemical equilibrium refers to. Now, when the rate of the forward reaction is equal to the rate of the reverse reaction, the state of chemical equilibrium is achieved by the system. Now, when there is no further change in the concentration of the reactant and the product due to the equal rate of the forward and reverse reaction, the system is said to be in a state of dynamic equilibrium. A state of dynamic equilibrium. Okay. So please, let's take note of that. Chemical equilibrium, dynamic equilibrium, and so on. So please, very important. Okay. Let's move along now and then look at all the things. We have types of chemical equilibrium now. Types of chemical equilibrium. There are basically two types of chemical equilibrium. We have the homogeneous equilibrium and the heterogeneous equilibrium. The homogeneous chemical equilibrium, in this type, the reactants and the products of the chemical equilibrium are all in the same phase. They exist in the same phase. So homogeneous equilibrium can be further divided into two types. We have reaction in which the number of molecules of the products is equal to the number of molecules of the reactants. For example, when hydrogen and iodine react, we can have such, and if you look at them, they are reacting in the same phase. You understand? They are both in gaseous phase. So that's an example of a chemical, of an homogeneous chemical equilibrium. The second one is when we have reaction in which the number of molecules of the product is not equal to the total number of the reactant molecule. For example, when you have your sulfur dioxide reacting further with oxygen to give us, XO3, you can see, it looks as if, there's a skew, in which the number of the molecules of the product is not equal to the total number of the reactant molecule. The same thing happens with the second example that is there. So that is, or these are homogeneous chemical equilibrium. Homogeneous chemical equilibrium. Okay, the second type is what we call the heterogeneous chemical equilibrium. In this type, the reactants and the products of chemical equilibrium are present in different phases. A few examples of heterogeneous equilibrium are given below. When you have CO2 in gaseous phase, reacting with carbon in solid phase to give us carbon-2 oxide, and that is in gaseous phase. That is an example of a heterogeneous chemical equilibrium. So the different types of chemical equilibrium are based on the phase of the reactant and the products. For homogeneous, they exist in the same phase. For heterogeneous, they exist in different phases. Okay, all right now. So let's push it further and talk about reversible reaction. And we say a reversible reaction is one in which the products can react to form the reactants. The product can react to form the reactant. So it's a forward and a backward reaction, whereby A plus B can equal to what C plus D, and C plus D can also give us what A plus B. That's what we call the reversible reaction. Now, examples: formation of ammonia, which through a process we call the Haber process. We have the nitrogen and hydrogen forming ammonia. So it's a forward-backward reaction, you know. Another example of reversible reaction is decomposition of calcium carbonate. When calcium carbonate decomposes, it can give us calcium oxide and carbon 4 oxide, and it can react again and give us calcium carbonate back again. So action of stain on iron is another example of a reversible reaction as stated in that on the screen there. Okay, so we'll push further and look at factors, you know, affecting chemical equilibrium. There are certain factors that affect chemical equilibrium, and I want to look at them one after the other. The French chemists Le Chatelier and Brun proposed certain generalizations to explain the influence of changes in temperature, concentration, or pressure on the state of an equilibrium state, you know, or sorry, a state of an equilibrium system. So when one of these parameters changes, the equilibrium of the system is disrupted, and the system readjusts itself until it returns to the equilibrium or returns to equilibrium. So Le Chatelier principle is the name of the generalization. And what does it state? Le Chatelier's principle says that a change in any of the components that determines a system's equilibrium conditions will move the equilibrium in such a way that the effect of the change is reduced or counteracted. So if there's a change in the product, if there's a distortion or a change in the product aspect in the product area, the equilibrium will also want to shift toward to the reactant side of the reaction, and vice versa as the case may be. Now, the following factors affect the chemical equilibria. The factors include concentration, pressure, temperature, catalyst, volume, addition of inert gas. So we're going to take them one after the other, and we'll look at them and how they affect chemical equilibrium. Okay. Now, when there's a change in concentration of any of the reactants or products in an equilibrium, reaction is altered and the equilibrium mixture composition changes to minimize the effects of the concentration change. Now, according to Le Chatelier's principle, the reaction that consumes the substance that is added reduces the concentration of the reactant or product added. Now, the reaction in the direction that replenishes the substance that is withdrawn reduces the concentration of the reactant or product removed. Okay, so that is based on the Le Chatelier's. Now, it may be concluded that increasing the concentration of one or all of the reactant species causes the equilibrium to shift forward. So it will shift forward, resulting in the formation of more products. When the concentration of one or more of the product species is increased, the equilibrium will do what? Will move backward, resulting in the formation of more reactants. So the composition of the mixture in chemical equilibrium changes when the concentration of the reactants or products is changed. Okay, good. So let's take note of that. So that is in terms of change in concentration. Let's move forward and look at change in temperature, which is another factor that affects chemical equilibrium. According to Le Chatelier's principle, if the temperature of an equilibrium system is increased, that is, when heat is supplied, the equilibrium will move in the direction of the added heat. With an increase in temperature, the equilibrium will move in the direction of an endothermic reaction. The decrease in temperature, on the other hand, will shift the reaction or will shift the equilibrium in the direction of the heat production, favoring exothermic reactions. Now, the effect of temperature on chemical equilibrium is determined by the reaction sign, that is, of delta H, according to Le Chatelier's principle. So, we can equally say this, that as the temperature increases, the equilibrium constant of an exothermic reaction decreases. As the equilibrium constant of an endothermic reaction increases, as the temperature increases. Now, let me say that again for emphasis sake. As the temperature increases, the equilibrium constant of an exothermic reaction will do what? Will decrease. Don't forget that exothermic reaction will always be giving heat to the environment. You get? Now, on the reverse side, the equilibrium constant of an endothermic reaction increases as the temperature increases. So when you increase temperature, what happens is that if it's an endothermic reaction, it will increase because it is, absorbed into the system. So that's that for that. So please, let's take note of that as it affects equilibrium constants, okay, or chemical equilibrium. Now, change in pressure on the other hand, let me just summarize this way and say that when pressure is increased, the reaction reverses because the number of moles of gas on the reactant side is decreased. When pressure is reduced, the reaction proceeds forward because the number of moles of gas on the product side is reduced. So that is one way in which pressure affects the chemical equilibrium. Okay, all right, see? So we look at the change in volume, and I would just want to summarize and say that when the volume of a gaseous mixture at equilibrium is reduced, the equilibrium will move in the direction of a smaller number of gaseous molecules. So if it is a product that has a smaller number of gaseous molecules, it will move in that direction. If it is a product, it will move in that direction. When the volume of a gaseous mixture at equilibrium is increased, the equilibrium will move in the direction of the large number of gaseous molecules. So we must understand this and understand the dynamics of changing volume and how it impacts or affects chemical equilibrium. Okay, all right. Also, introduction of catalyst, the effect of catalyst now. Now, the equilibrium is unaffected by the catalyst. This is because the catalyst favors both forward and backward reactions equally. As a result, the forward to reverse rate ratio remains unchanged, and there is no net change in the relative number of reactant and product present at equilibrium. Thus, a catalyst has no effect on equilibrium position. As a result, a catalyst has no impact on chemical equilibrium. It simply accelerates a reaction. So a catalyst in general speeds up both forward and reverse reaction. Therefore, the reaction reaches equilibrium more quickly. And that's that for that. Okay, so we move on now to the next one, which is the effect of the addition of an inert gas. Depending on the conditions, adding inert gas to equilibrium has the following effects. Addition of inert gas at constant volume. When you add inert gas to a chemical equilibrium at constant volume, when a constant volume of inert gas is added to the equilibrium system, the total pressure increases. The concentrations of the reactants and products on the other hand will remain unchanged. As a result, there will be no effect on equilibrium under this condition. Now, the reverse happens when inert gas is added at constant pressure. When at constant pressure, an inert gas is added to the equilibrium system, the volume increases. As a result, the number of moles per unit volume of various reactants and products will decrease. So the equilibrium will shift in favor of an increase in the number of moles of gases. So we must note this and understand the dynamics when this variation, is set in. Okay, so those are the factors affecting chemical equilibrium. And we'll move along by looking at examples using Le Chatelier's principle. So we want to look at some examples using Le Chatelier's principle. Haber process, which leads to the formation of ammonia, is an example. Increasing the pressure or lowering the temperature favors ammonia formation. So when you increase the pressure and you lower the temperature, you will favor ammonia formation in this regard. So don't forget what I said. When we're talking about, pressure effects, volume effects, and temperature effects on um on the chemical equilibrium. So action of steam on ion is another one. So when you add steam or remove hydrogen, sorry, when you adding steam or removing hydrogen, shift the reaction to the right. That is, it will favor the product formation. So these are examples using Le Chatelier's principle. Okay, so the next thing we need to look at is the equilibrium constant. The equilibrium constant, K. It expresses the relationship between products and reactants of a reaction at equilibrium with respect to a specific unit. An equilibrium state is achieved when the forward reaction rate equals the reverse reaction rate under a given set of conditions. Under a given set of conditions. Okay, so let's pause a little and reflect on that briefly before I continue. Okay, so like I was saying, I said we should pause and reflect on that. So an equilibrium state is achieved when the forward reaction rate equals the what? The reverse reaction rate under a given set of condition. So there must be a relationship between the composition of the system at equilibrium and the kinetics of a reaction represented by the rate constant. We can show this relationship using the decomposition of N2O4 to NO2. Both the forward and reverse reactions for this system consist of a single elementary reaction. So the reaction rates are as follows. So we look at it together. You have the reaction going forward, backward, and forward, leading to the formation of NO2. The forward rate is the formation constant, which is of the N2O4, and then the reverse, sorry, the formation the forward sorry, please, let's take that again. For the forward rate, we have the that of N2O4, and then for the reverse rate, we have the constant for NO2 raised to power 2. And the reason why we are doing raised to power 2 is because there's a 2 that is in front of NO2. So it will be raised to power 2. So at equilibrium, the forward rate equals the reverse rate, So the forward rate equals the reverse rate. And it then connotes that what's it called? Equilibrium constant for the reactant side will be equal to the equilibrium constant for the product side. So when you look at these together, it means that the constant for the forward and the reverse reaction will be equal to NO2 raised to power 2 divided by N2O4. Okay, so the ratio of the rate constants gives us a new constant, which we call the equilibrium constant, which is defined by K, which is what? Kf over Kr. That's the forward and the equilibrium constant for the forward reaction and for the reverse reaction. Hence, there's a fundamental relationship between chemical kinetics and chemical equilibrium under a given set of conditions. The composition of the equilibrium mixture is determined by the magnitude of the rate constant for the forward and the reverse reaction. So the equilibrium constant is equal to the rate constant for the forward reaction divided by the rate constant for the reverse reaction. And that was what we did here, So that is what we typified, or we use this equation or this formula to represent. Okay. All right. Having said that, we need to develop an equilibrium constant expression. So how do we develop an expression for the equilibrium constant? Equilibrium constant? No. Now, for any reversible reaction of the general form, A, that's the coefficient, A plus B with a B coefficient, resulting to C plus D with C coefficient and D coefficient, as the case may be, where A and B are reactants, C and D are products, A, B, C, and D are the stoichiometric coefficients in the balanced chemical equation for the reaction. The ratio of the products of the equilibrium concentration of the products raised to their coefficients in the balanced chemical equation to the product of the equilibrium concentrations of the reactants raised to their coefficients in the balanced chemical equation is always constant under a given set of conditions. Now, this relationship is known as the law of mass action or law of chemical equilibrium and can be stated as follows. The equilibrium constant K equals to what? The concentration of C raised to pi its coefficient, the concentration of D raised to pi its coefficient, divided by the concentration of A, which is the reactant raised to its coefficient, and the second reactant, which is concentration of B raised to the power of its coefficient, which is a small b. So the highlighted equation is called the equilibrium constant expression. So that's how we express the equilibrium constant. So when you look at it critically, you look at it that it is the product, the products and their coefficients, divided by the product of the reactants and their coefficients. Okay. All right. So that's that for that. So let's quickly summarize this lesson. And we've been able to talk about equilibrium, chemical equilibrium, and how it occurs in reversible reaction. We have looked at dynamic equilibrium. We have also looked at Le Chatelier's principles. We have a principle, pardon me. We've stated what Le Chatelier principle is, and we've talked about the factors that affect chemical equilibrium. And we've also touched on the equilibrium constant expression. So we have tried to fashion out an expression for the equilibrium constant. We did not stop there. We also looked at the equilibrium constants when we have with coefficients and so on and so forth. So we have been able to look at all this. We've looked at the examples of reactions from Le Chatelier's principles, looking at Haber process and then the action of steam on iron and so on and so forth. So we have been able to do that. So if you have any question based on what you have discussed so far, please let me know in the comment section, and then I will do justice or react to it appropriately. Okay, so let's evaluate this lesson, and we have those questions that have been highlighted to evaluate the lesson. I'll just speak on some of them. You can always look at them at your leisure and answer them, and you can tell me by sending the answer to the comment section to let me know what you discovered when you interacted with the question. This first one says chemical equilibrium is said to be achieved when all reactants are converted to products, the forward reaction stops, the rate of forward and reverse reactions are equal, and then the concentration of products is 0. So which of the following reactions represents a heterogeneous equilibrium? So what I want you to do is just look at the questions and then look at the options. Tell me what you feel the answers are in the comment section. So look at them carefully and let me know what the answers to these questions are in the comment section, and then I will respond to it by telling you whether you're right or whether you're wrong, and so I will be able to know whether you've gotten a grasp of the lesson as I've taught it this today. So please do well to interact with the questions, and let's have your feedback, or let me have your feedback, please, from the options that are listed on the screen. Okay, thank you very much. So these are all the questions that you can also look at and interact appropriately. Okay, all righty. So please look at these questions one after the other, and ensure that you attempt them. It's important that you attempt answering the questions, and let me have your answer in the comment section, and I will let you know if you're right or if you're wrong. Okay, so let's look at that. Let's look at it. Very important. Okay, thank you very much for listening and for watching. And I hope you've gotten a lot from the lesson that I've shared with you so far. Please, if you have any question, you have an area that you're not so clear about, please let me know in the comment section, and I will do justice to it by giving a feedback that is appropriate. Thank you once again for listening. I'll see you in the next video.